So this example is a mesh analysis example. We have a circuit here with 8 resistors and 3 voltage sources. So we have multiple voltage sources, and we have 5 loops, which I've already labeled loop A, loop B, loop C, loop D, and loop E. So what we're going to do here is we're going to study or analyze the input. So we'll see, we're going to solve for the loop currents, and so we're going to build up our matrices. So we have our resistance matrix, which is going to be a 5 by 5 because there's 5 loops. Then of course we have our loop currents, and we're going to have our voltages. Now our loop currents, we have 5 loops, so we're going to have a loop current IA, and a loop current IB, loop current IC, and a loop current ID, and of course a loop current IE. So those are our loop currents. So when we start analyzing our resistance matrix, we're going to be looking at, I've already kind of laid this out. We have 5 by 5, so we have A, B, C, D, and E. And then down the side, again, we have A, B, C, D, and E. So what you're looking at is when you look down and you have an A and an A, or a B and a B, or a C and a C, row and column, a D and a D, an E and an E. This is the diagonal, and these are always going to be positive values. And then the off diagonal, which is this triangle here and this triangle here, all of this is going to be negative. So let's take a look here, and the first thing we want to do, you can do voltages first, or you can do resistances first. It doesn't really matter. Remember, when you're doing mesh analysis, if you do have a current source, you first must convert that current source into a voltage source to do the mesh analysis. Okay. So when we look at this, we see our loop A has a resistor R1 and a resistor R2. So that is R1 plus R2, and so that's 8K plus 2K, so that's going to be a 10K. And then as we go across the row now, we need to subtract all the resistors that are touching other loops. So you see here we've got loop A is going down through resistor R2, but loop B then is going to be going up through that. So those two are opposing each other. So we now have to subtract R2. So we subtract R2, which of course would be 0 or minus 0 if you want to be technically correct, but I'm just going to put the 0 in there. And then you look and you see that loop A is touching loop D, but there's no resistance. It's just this one node here where they're actually touching. So, and the other two loops, C and E, are just out here. They're not touching A in any way. So those are just going to be zeros. Okay. Whoop. I'm sorry. I subtracted R2. R2 should be 2K. I should be subtracting 2K here. Sorry about that. And then those are just all zeros. So now we're going to do loop B. And just rewrite this a minute. So this was 10K, and this was minus R2, which was a 2K, and then 0, 0, 0. Alright, so now you really want to work clockwise. Just always be consistent and work clockwise, or at least work in a consistent manner and keep track of where you're at. Okay, so I'm gonna do B here, and so we need to look at all the resistors in loop B. So that is going to be R2 plus R4 plus R8, R2 plus R4 plus R8. So notice that we do that in the column that matches the B. Okay, so we add up all the resistors touching this loop and put them in this matrix spot. So we have the R2, the R4, and the R8 are all in loop B. And so that's going to be 2K plus 3K plus 2K. So that's going to be 7K. So that's a positive 7K. And now we want to start subtracting. Well, we kind of already said, right, R2 is touching both A and B, so those are opposing. So this is going to be a minus R2 over here, which would be a 2K. And then B and C are touching at R4. B and C are touching at R4. So in the BC spot here, we're going to subtract R4, which is a 3K. And for the for this, we've got D is touching, the R8 is touching, so we're going to subtract off an R8, which is a 2K. And B and E do touch, but they only touch at that one point, so there's no resistance, so we put a 0 in there. Alright, so looking at loop C, so loop C here is touching two resistors, R3 and R4. So again, we find the spot where the column C and the row C touch, and we're going to have, those are going to be a plus R3 and a plus R4, which is going to be a 3K and a 6K. So that's going to be 9K. And then we're going to subtract off. Well, loop A doesn't touch loop C in any way, so that's simply 0. Okay. Loop B, as we already said, loop B touches with this 3K R4. So we subtract R4, which is a minus 3K. And I just noticed I missed my minus signs here. So you always want to go back and double check, which I will do once I'm complete. But remember that the only positives should be along your diagonal, and all the other values should be negative. So I missed that negative there also. And so now we're going to do D. Well, C and D only touch at that node, so there's nothing else touching there. So that's going to be a 0. And then C and E. Now C and E do touch and they share a voltage source, but they do not share a resistance. So that's a 0. So now we're going to look at at loop D. Loop D here has, we're going to look at column D and row D. column D and row D here is where we're going to put these. We're going to look at all the resistors that are touching loop D. And so that's R5 plus R6 plus R8. I mean, I just putting them in numerical order here. I mean, but as you go around, where you see R8, R6, and R5, which is actually reverse numerical order. But we're going to put this in here now. So that's a 2K plus a 6K plus an 8K. So 2 and 8 is 10 plus another 6, so that's going to be a 16K. And again, this is the positive because this is the spot where the column and the row are both the same letter, so that one's positive. Now we're going to look, and we see that D touches A here. D touches A only at that point, so DA gets a 0. B and D touch at R8. Okay. So B and D touch at R8, so that's going to be a minus R8 here, which is a minus 2K. And then C and D only touch at that node, so there's no resistance they share. So again, that's a 0. And then D and E are sharing R6, so we're going to subtract off R6. We're going to subtract off R6 here, which is 6K. So again, that's a minus 6K. And then we just need to do E. Okay, so we see E here, and we go around the loop of E, and we see that it's touching R6 and R7. So E to E is a positive, so that's R6 to R7 plus R6 plus R7. Okay. And so R6 is a 6K and R7 is a 3K, so that gives me a 9K. And then we look to see what to subtract off. Well, loop A and E do not touch at all, so that's a 0. Loop B and E only touch at that one point, so that's also a 0. So EA and EB are both 0. C and E share this conductor here with this voltage source, but there's no resistance in here. There's no resistance. So the resistance piece, which this is the resistance matrix, it is also 0. And then, as we already said, D and E share R6, so we have to subtract R6, which is a 6K. So remember here, now if we look at this, and we look at the diagonal, or the off diagonal here, okay, the diagonal values are all positive. So this is positive, this is positive, this is positive, this is positive, and this is positive. And then when we look here, we see on the off diagonal, we see -2 and -2. We see a -3 and a -3. Here, we see a -2 and a -2, which is R8. And here we just see zeros. And then here we see a -6 and a -6. Now, doing this, I double checked and I see that I forgot to put my negative sign right there on that one. So, you know, you always want to go back and double check this and make sure you got your positive and your negative signs correctly once you build your matrix up. All right, so now we've got our resistance matrix. We need to look at our voltage sources. Okay, so we have E1 only touches loop A. It does not touch any other loops, only loop A. And it is pushing, the positive is pushing in the direction that we declared the loop current. Now remember, the loop currents, we pick the initial direction of those. And so we always pick those to be clockwise. And if it turns out that the current happens to be flowing counterclockwise through that particular loop, then we'll get a negative sign. So when we solve this, if we get a negative current, that tells us that our initial assumption of a clockwise current through that loop turned out to be negative. And that's all that means. So we always declare clockwise loop currents and we solve it. So again, E1 is the only source touching loop A. And so therefore we'll just put 100 volts here. And that is all. B, here's loop B. Loop B only has a 20 volt source. And that 20 volt source is pushing in the same direction as B. So therefore we're going to have a positive E2, which is 20 volts. Loop C, here, loop C has a 30 volt supply, E3, but E3 is pushing out this way and up counterclockwise. Okay, so it's opposing the loop C current, and so therefore we'll put minus E3. We're going to subtract minus E3 here, so it's going to be a minus 30 volts in the C column. So remember, this here is our C column here. And so that's, we look at all the voltage sources. Now, just, I didn't put one in here, but let's just say that we had a second voltage source up here that was, say, 10 volts or something, but it's pushing clockwise in loop C. Well, if that was the case, call this one E4. E4 is opposing E3, so our voltage would be E4 minus E3, because E3 is going in the opposite direction of our loop current. And so therefore, if we had this extra voltage source up here, we would have 10 volts minus the 30 volts, which would give us a total of 20 volts. And so in this spot here, if that was our case, in this spot for the C column, we would put a minus 20. All right. So I just wanted to cover that case in case you can have two voltage sources in the same loop and you just algebraically add those. So if they're opposing each other, you actually subtract them. If the ones that are pushing in the direction of the loop current, those are positive sources, and the ones that are pushing against the loop current would get a negative sign. All right, so now we're at loop D. So here is our loop D. Loop D doesn't have any voltage sources, only resistances. So we come to D, and that's simply going to be a 0. Okay, so there are no voltage sources. Just abbreviate that. And so that's simply a 0. And then E has also got loop E also has supply E3, this 30 volt supply, but here the 30 volt supply is pushing in the same direction as E. And so therefore E is a plus E3. And so that's going to be a positive 30 volts. So there is our layout. So now remember, this is basically resistance matrix R times a loop current I is equal to a voltage V. And so when you set this up, you effectively end up with something like Ohm's law. R times I equals V. But this will solve all the voltages and all the currents in here. So now we need to use some sort of calculator program. I prefer the octave program. And so let me open that. Alright, so here's my octave program, and the first thing I recommend that you do, in case you had this program open before, is to run the clear command to clear all the variables. And then you could also run the CLC, which will clear the command window, which is what we're looking at here. And so now I'm going to build my R matrix, my resistance matrix, which is going to be, I'm just getting this right over here. I'm just going to do every row and then the next row and the next row and the next row. And so we're going to have R10, comma, minus 2, comma, 0, comma, 0, comma, 0. Now you could put a semicolon in here, or you could actually just hit enter and put it on the next line. So I'm going to do that. Minus 2, comma, 7. Now notice I'm not putting the K's in here. Remember that all my resistors are kiloohms, so if I leave out the K's, I just have to remember that my loop currents then will be milliamperes. Okay, so I'm leaving those off, and I just have to remember that my currents are going to be milliamperes. So we have minus 2 plus 7 minus 3 minus 2, 0. That's the second row. The third row is 0, comma, minus 3, comma, 9, comma, 0, comma, 0. The fourth row is 0, comma, minus 2, comma, 0, comma, positive 16, comma, minus 6. And then the fifth row is 0, comma, 0, comma, 0, comma, minus 6, and 9. Alright, so there is my matrix. Okay, and let me just kind of pop that over here for a minute. Alright, so here is my R matrix. I just want to remind you, right, so as we look at this, everything on the diagonal is positive. Everything on the aft diagonal is negative, and it's symmetric. Everything is symmetric in here. So we can see that when we look at this software program, we can see, positive, 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 positive along the diagonal, and then the off diagonal values are either zeros or negatives, and they're also symmetric, so they match top and bottom. You just flip the triangle and they match. Alright, so now we need to build our V. So let me slide this over here a little bit. So here's my V matrix. So the V matrix
is just a column matrix, so I can do 100. I can't put semicolons and put them on a row, but I can just either hit enter and just put in here 20, minus 30, 0, and positive 30. And then close my bracket. So there is my V. So we have 10, 20, minus 30, 0, and positive 30. So now we can declare our loop currents. I is equal to R, and then we use this backslash V because it's V divided by R. So this kind of gives the impression that the V and V is on top and R is underneath. So it's I equals R backslash V. And that gives us our loop currents. Now remember, these loop currents are in milliamperes. And so we have the first one here is the 11.2658 with 6 significant digits. That's just the way the Octave software does it. So I have IA is equal to the first value. And then we can say IB is equal to the second value. And IC is equal to the third value. And so on, so we can separate these out. Now notice that IC is negative. Okay, IC is actually negative. Well, let's come back and look at our circuit. And remember here in this circuit, we have loop C. Loop C here is defined as going clockwise, but it's got this 30 volt inside it that's pushing the opposite direction. And because of this 30 volt in here, it's actually turns out that it's negative, so the current IC is negative. What that means is that the current through the resistor R4 is equal to IB plus IC, the magnitude of IC. Okay, so that because both IC is going this direction and IB is going this direction. So if I wanted to calculate the voltage across R4, it would be IB minus IC, but IC is negative, so that makes it a positive. So we're going to find the voltage across R4 here, okay, which using Ohm's law, we get that the voltage V4, which is the voltage drop with a positive on top, that's how I'm defining it, V4 is going to be IB minus IC. So it's IB minus IC, and of course this is Ohm's law, so then we have to multiply it times the resistance R4. Okay, so but IB is 6.3291, and then minus IC, but IC is a minus 1.2236. And then all of this then is multiplied times the 3 kilo ohms. Now remember, the currents are in milliamperes. Okay, I is in milliamperes, and the resistors are in K, so K kilo ohms times milliamperes just gives me straight volts. So this gives me a voltage of 22.658 volts. So this is 22.658 volts. And then the voltage V3, again, I'm defining it with the positive on top, so that is IC times the
or excuse me, yeah, IC times R3, Ohm's law. So that is IC, but IC is a negative 1.2236. 2236 times the 6K ohms. Now remember, this was milli. These currents up here were milli. Let's put the M's in there so we have it.
All right, and so to calculate that, then we have that V3 is equal to IC times the 6K,
which is a minus. Okay, so this is a negative voltage because I defined the positive side up top. So this is a minus 7.3418. All right, so now if we just go around this one loop right here, okay, I'm just going to go around this one loop. I get, if you start at this point, you're going to go up V4, so it's going to be plus V4, and then it's going to be minus V3, and then it's going to be minus E3, and that all must equal to 0 according to Kirchhoff's voltage law.
that must equal to 0 according to Kirchhoff's voltage law. So if we add these values up,
we get the 22.658 minus, because I've defined it as the positive on top, right? But remember that it actually turned out to be a negative over here. And so it's a minus 7.3418 minus E3, which was 30, and that all must equal to 0. Okay, so just roughly looking at this, we got 22.658 minus a minus, so that's a plus 6.58 and minus 7.34, right? We add those two together, that's of course going to be 30 volts. So let's just do it. If we use the Octave software, we can do it in high quality. If we do high precision, our V4 plus V3 must equal, V4 minus V3 must equal 30 volts. Okay, and so you can see that does work. So remember, it was defined as V4 minus V3, and that is in fact 30 volts. So you subtract off the 30 volt source and you have 0 volts, and that satisfies Kirchhoff's voltage law, which tells me that my calculations were correct. So you can pick any single loop after you do mesh analysis. You can pick any single loop and apply Kirchhoff's voltage law to that loop using your found currents, your found loop currents, to determine the voltages, and you should get 0 volts. And that will verify that all your calculations and all your entries, when you typed it into your calculator software, all of that was correct. If it doesn't add up to 0, if even one of those loops doesn't add up to 0, then Kirchhoff's voltage law would not be satisfied, and so therefore you must have made a mistake. All right, so but you only need to pick one loop, and you can double check that.